Okay, in this one I'm going to showcase the mlock syscall by showing how you can improve the performance of some applications with it, and it can also improve security in some cases as well. So what mlock does is that it prevents some of your memory from going into swap. If you don't know, the swap is just kind of where memory goes if you don't have any more space in RAM anymore. So it's just on disk, and it will use the disk as memory, which is obviously nice if you're running out of memory and you don't want your application to just die, but it's also extremely slow. So for some applications, you want to say to the kernel, never put my pages to memory, to swap. So here I have just a little main where I allocate some memory. I allocate 700 megabytes of it. I just do some operations on it. I write a bunch of time to it, and then I deallocate it. And that's all. And we can see that here I have a little container where there is 1 gig of RAM and 1 gig of swap. And since I have 700 megabytes, some of this data is going to need to go to the swap. So if I do this, we can see that they will not finish at the same time, even though, I mean, obviously I started them at different times, but you can see that the first one takes much longer because this guy allocates a bunch of stuff into RAM, and then this guy allocates on like again, and so it's kind of pushing out the memory that this guy had in RAM, and it's putting it in the swap, which is disk, so this one becomes slow. And we can do the opposite, and we will see that this guy will finish after. So anyway, let's now fix that with mlock. So the way I'm just gonna do this is very simple. I'm just gonna say that yeah, if the first argument of my program is mlock, I will lock the data. Yeah, this is how you call the mlock syscall. You just give it a pointer to the start of your data and the size of the data that you want to lock into RAM. And so, yeah, and return 0 if it worked. So let's compile this, like so. By the way, you see my previous example works. And now, now if I call the first one with mlock, but the second one without mlock, this one is going to be forced to go in the swap, and this one is going to finish much faster. And so this works the other way around as well. If I start this guy first and then this guy, this one should still finish much faster because it's gonna now push this guy to the swap. So yeah, there you go. So yeah, this is one way if you have a like a time critical, latency critical application, and you have a yeah, you want your memory to absolutely stay in the RAM at all cost, and maybe like because maybe you have like your latency critical application, and then you have on the same server you have some database or some cache or some monitoring tools and so on, and you obviously don't want all of these auxiliary services to push memory from your application into swap if they go crazy. So what you can do is start your application and mlock your data, and then you will be guaranteed that this data will never go into swap, and so it will never be slow. Well, it will never be as slow as the disk. So yeah, that's pretty much it. Obviously, this also works if you have an application. For example, I know the HashiCorp Vault does this, where you have some I don't know, critical security things like passwords or tokens or and so on, which you want to avoid spreading around. Well, you can just mlock the part of your memory which contains the passwords or the token in them, do your manipulation on there, and then it's much safer because an attacker can't like push this password or token data into the swap, and then the swap is just something, it's just on disk, you know, so like, I don't know, there is more surface of attack. Anyway, one last thing I wanted to show is that there is mlock and munlock. Yeah, I didn't use munlock, but obviously if you lock some memory after you after, I don't know, if I don't know in what scenario you would use this, but you can also unlock it, so allow it to go back to swap. And there is these two syscall which seem a bit more useful for like, I don't know, the general case. It's mlock all and munlock all. And what it does is that unlike mlock, where you need to specify the address and the size, with mlock all, what you can do is start your application with mlock all like this, and you can your flag, with your flag, we can say all the current pages will be locked. So this could be here actually, like so, and this will be the same behavior as before. So yeah, actually, let's do that to prove that it works. So let's lock that one and not lock that one. And so this one, the locked one, finished faster than the other one, as expected. So this basically says like every single page of memory which is mapped by my process, all of that should be locked. And what you can do, which is even cooler, is that you can put that at the very start, and you can use the future flag, which means all future page that I allocate will be locked in memory, which is very useful because obviously if your application does, I don't know, 50,000 mallocks, you know, you're not using mmap or anything, and you don't want any of this memory to ever go to swap, you can just say, for all future allocations, never put that into swap. Let's recompile. And again, we should see the same behavior where the locked one finishes much faster. Yeah, there you go. So yeah, that's about it. And I hope you learn a few tricks and you learn to keep your time-sensitive application a bit safer than a bit safer against like random latency spiked caused by some application like hogging most of the memory on your system. And I'll see you in the next one.